Today we want to go hit the Wayback Machine a little bit and go back and look at geometric series in more detail. For those of you following along in the book, geometric series is way back in chapter 9, specifically chapter 9, section 2. If you weren't aware that geometric series were in chapter 9, section 2, then you are a few homework assignments behind, and you should start getting caught up. It's interesting to look at geometric series after we've looked at power series and after we've looked at the ratio test. So we're going back to geometric series, just a series. There's no variable x. We're not trying to find an interval of convergence. We're just trying to determine if a series converges. So under what conditions is a times r to the n a finite sum? We can see already that this is entirely going to hinge on r. If we think about the coefficient a, that's not going to affect the convergence or divergence. We can't multiply our way into convergence from divergence, and we can't multiply our way out of convergence when we're multiplying by a constant. So it's really going to hinge on what the value of r is equal to. If we think about the ratio test, we can see that the absolute value of r needs to be less than 1. And we're going to have divergence at the endpoints when r is plus or minus 1. Because we have the ratio test now, and we see that r to the n, is the exponential factor. So when we run that through the ratio test, this series is going to leave behind an r. So if the limit from the ratio test needs to be less than 1, that means r needs to be less than 1. So if we do a ratio test, so in a ratio test, the nth term will be just a times r to the n, and the n plus first term is a times r to the n plus 1. So experience on the ratio test paying off. We can see that the limit from the ratio test is going to be r. N completely drops out of everything. The a's cancel out. R to the n plus 1 divided by r to the n is going to leave us behind an absolute value of r. And it's going to be the limit as n goes to infinity of just 1. So once we simplify r to the n plus 1 over r, that leaves behind an absolute value of r that's no longer involved with n. Everything else is canceled out. So just like our experience from the ratio test told us that the limit from the ratio test was going to be absolute value of r, here we are making sure that that works out. The ratio test says the series is absolutely convergent if the limit from the ratio test is less than 1. So if the absolute value of r is less than 1, then our geometric series is absolutely convergent. So a geometric series converges if the absolute value of the common ratio is less than 1. So a series like 5 times 1/2 to the n is absolutely convergent. A series 1/2 times 5 to the n diverges. The common ratio is the thing that's being raised to the n power. If the thing being raised to the n power is strictly less than 1 in absolute value, then the series is absolutely convergent. Not only does it have a sum, it has one sum. So like a conditionally convergent series, that'll have a different sum if we start rearranging the terms. Should remember that the common ratio needs to be less than 1 in absolute value. So it's okay if the common ratio is a negative 0.4. 0.4 is less than 1. The series is absolutely convergent. We want to emphasize that the absolute value of the common ratio is less than 1, not just the common ratio is less than 1. Because if the common ratio is, let's say, -3, -3 is less than 1, but the absolute value of -3 is greater than 1. The reason I'm pointing this out is that a lot of times I'm going to be lazy and I'm going to say that the common ratio needs to be less than 1. And what I mean is that the common ratio needs to be less than 1 in absolute value. That's kind of a way to phrase it. The absolute value of the common ratio needs to be less than 1. The fact that I've built this habit of saying an absolute value at the end of the sentence where it doesn't belong instead of in the middle of the sentence where it does indicates that I forget to do this a lot. Questions? One of the cool things about geometric series is that we can actually find the sum of a geometric series. If it's infinite, we can find the sum if it converges. And it's kind of interesting how we get at the sum. We start by looking at a finite geometric series. Here's a maneuver that we should see, because we kind of used this maneuver a little bit before. So here we have a finite geometric series with n terms. Notice that we started our counting at 0. That first term a is a times r to the 0 power, a times r to the first. So when I write n terms, I have a times r to the n minus 1. So I have n terms with a common ratio of r. Right now, we don't know what the sum is, so we're just going to say, but we know that there is a sum, so I'm just going to call it S. We don't know the sum yet, but we know that there is a sum. We don't have to worry about convergence because we are looking at a finite geometric series. So now at this point, it doesn't matter what R is. We got n terms with a common ratio of R. I'm going to multiply both sides by the common ratio. Now we start our algebraic chicanery. So I'm just going to multiply everything by r. This means the first term will be AR, then AR squared, then AR to the third. And then the last term will be AR to the n. If I multiply everything on the left by r, I multiply everything on the right by r. Now I'm going to subtract. So if I label this as line 1 and label this as line 2, we're going to subtract. I'm going to take line 2 and we're going to subtract line 1. So I have RS minus S. I want to do it the other way around. It doesn't really matter because we're just multiplying by -1. But I'm going to drop into habits where I write things the other way around, and you're all going to wonder why I switched. So let's take line 1 and subtract line 2. So if on the right side, that's going to look like S minus RS. And on the left, I'm going to have all these terms, and I'm going to subtract all the terms from line 1 and subtract all the terms from line 2. So I'm going to have A plus AR plus AR squared and from this, we're going to subtract all terms from the second line. What we're going to notice, I don't have enough space to write it here, so I'm just going to randomly write it underneath. And secretly line up the things that are going to cancel out. What we'll notice is that the only two terms that line one and line two don't have in common are the first term from line one, the A, and the last term from line two, AR to the N. Everything else is going to cancel out because we're subtracting. So I take the AR from line one, and that'll cancel out the second term from line one, cancels out the first term from line two. The third term from line one cancels out the second term from line two. The nth term from line one cancels out the n minus first term from line two. The only ones that they don't have in common are A and AR to the N. Those are the only two terms that line one and two don't have in common. Everything else cancels out. It's similar to the maneuver that we did with the alternating harmonic series, where we multiplied by something, then we started lining things up. A little different in this case because we have a finite number of terms. So we don't have to worry about things like convergence, absolute or otherwise. But now if we look at what's left over, on the left we have S minus RS, and on the right I have A minus AR to the N. So on the left side, the new left side, I've got S minus RS. And on the right, I have A minus AR to the N because everything else canceled out. The point of this exercise was to figure out what the sum of the series was, so that means solve for S. The point was to try to find the sum of the series. So now we're going to solve for S. To do that, we're going to factor out the S. That leaves behind a 1 minus R. Over here, we're going to factor out the A, just to make things clean up a little bit. We're looking for S, so now we just divide by the coefficient 1 minus R. So S is the sum of a geometric series where A is the first term R is the common ratio and N is the number of terms. So A is the first term of the series, not necessarily the coefficient that we see in all the terms. So A is specifically the first term of the series. R is the common ratio. And N is the number of terms. We want to identify A as the first term and not as the coefficient. Because if we set up a series where the indexing doesn't start off at 0, then the first term is not just going to be the coefficient. So this usually raises the question, why the first term? Why am I calling it the first term and not the coefficient? Oops. I wanted a finite. So in this case, we have a finite geometric series. The first term is 5 because the indexing started off at 0. The common ratio is 0.3, and there are 11 terms because the indexing started at 0. We don't normally start our counting at 0. We got to pay attention to the number of terms. So N is 11 terms for the indexing starts. So we have a finite geometric series. We can find the sum by using our handy formula. The sum is the first term times 1 minus the common ratio to the number of terms divided by 1 minus the common ratio. Hopefully I punched that in my calculator correctly. Just realized I left my graphing calculator, which is better at these kind of things, even though graphing calculators are terrible at graphing. They're really good at this kind of calculation. You don't have to have all this stuff in the middle. You just type it like you see it. So notice the difference between this this series where the indexing starts at 0, and so the first term is 5, and let's say starting off at 2. Here, our first term is not just the coefficient 5 because the indexing starts at 2. The first term is 5 times 0.3 squared. Because the index starts at 2. The common ratio is still 0.3. And the number of terms is still 11. Two is first, so 12 is 11. Twelve minus 2 is 10 gaps. That leaves 11 posts. So the sum will be different. Instead of the first term of just 5, I'm going to have to write 5 times 0.3 squared times 1 minus 0.3 to the 11th. This one will be a little bit less. Any questions? So that's why I'm calling it, I'm saying the first term and not the coefficient. That's also why I'm not just saying A all the time. We build it out of habits, like we talked about the Pythagorean theorem being A squared plus B squared equals C squared, which only works if we all agree that C is going to be the hypotenuse. If I draw a right triangle where A is the hypotenuse and B and C are the legs, then it's B squared plus C squared equals A squared. So we got to get used to things being different. Also, the C squared that we usually cite in the Pythagorean theorem is not the same C squared that we get in E equals MC squared. That's a completely different C squared. So we use these common letters for things, but that's only because we like to sound smart by reciting formulas. I don't know why that's the case, but let's talk about some cool algebra that's going on here. So we see that A plus AR plus AR squared is what we just found. We have a first term of A, a common ratio of R and N terms. Then we found the formula for the sum of that finite geometric series. Recall that this series is absolutely convergent if the common ratio is less than 1. If the absolute value of the common ratio is less than 1. I told you I was going to do that, so you'd be not surprised. Take this finite series to an infinite series. That's just taking the limit as n goes to infinity. We can see that if n is going to infinity, the base r needs to be less than 1 for the limit to exist. If the common ratio is less than 1 in absolute value, that's what the ratio test said would give us absolute convergence. And that's also what's required for this limit to exist. If the common ratio is less than 1, then I raise something less than 1 to infinity, and we'll end up with 0. So that 1 minus r to the n becomes 0. 1 minus 0, or 1. So now the sum of an infinite geometric series is a over 1 minus r if the common ratio is less than 1. What's that, 50 over 7? What? So notice that this is 7 and 1/7. Otherwise known as 7.142857 repeating. So 5 significant figures, that would be 7.1429. And so we can see that those, after the first 11 terms, the terms from 11 on out to infinity don't add up to very much on this scale. So there's 10,000. That's all. That the only start mattering at the 10,000 decimal place. But just like before, A is not the coefficient. A is the first term of the series. So if, for example, we started our series off at 2 and went to infinity, the first term would be 5 times 0.3 squared. And so our sum would not be 5 over 1 minus 0.3. It'd be 5 times 0.3 squared over 1 minus 0.3. Any questions? How's everybody okay? Geometric series? Okay, all good, everything cool? $45 over 70? Take out a 5. Every once in a while, I check. I usually find out that I can't. But I like to goof around numbers anyway. How's everybody okay? There's one more thing I want to point out. Not because it's going to help us find the sum of a geometric series, finite or infinite. We've already got the answer to that. There's no trick to it. It's just a simple trick. It's a formula. There's just something I want to point out in the formula. So take a look at what we have up here. If I take both of this equation and I drop out the a, I divide everything by a, I can get that 1 minus r to the n over 1 minus r is equal to 1 plus r squared up to r n minus r to the n minus 1. Earlier, when I was going to start off by doing 2 minus 1 instead of 1 minus 2, this is where I was headed. But then I decided I really wanted the formula to come out 1 minus r to the n over 1 minus r. So we don't have to worry about all of these negatives. But notice if I multiply the top and bottom by -1, I can write this as r to the n minus 1 over r minus 1. Now, this is a really strange thing to do. I tend to be in the habit of writing my polynomials from the constant up rather than the leading term down. But it's helpful to do this in this case because this is just a multiplication and division problem. If we divide r to the n minus 1 by r minus 1, we should get 1 plus r squared plus r cubed and so on. That also means if I multiply r minus 1 times this polynomial, I should end up with 1 minus, or r to the n, I should end up with r to the n minus 1. So there's a division and a multiplication that is sitting here. The multiplication is pretty easy to sort out, but if we divide, there's a bunch of zero terms. Oops. That's zeros. We could make the same point for the multiplication, but the multiplication step is really easy. It's just a lot of multiplication. I never pass up a chance to do some long division with polynomials. So if we start dividing, I think how many times can I subtract r from r to the n? I can do that r to the n minus 1 times. And so when I multiply, I get r to the n minus 1 minus r to the n minus 1. Oops, r to the n plus 1, minus 1 plus 1. I get r to the n minus r to the n minus 1. Now we're subtracting, and that cancels out the r to the n and leaves us with an r to the n minus 1. Then we just got to think, how many times can we subtract r from r to the n minus 1 without going negative? And we can do that n minus 2 times. So if I multiply r to the n minus 2 times r minus 1, I get r to the n minus 1 minus r to the n minus 2. We're still subtracting this from so we can see the long division is going to tell us the same thing. We can also multiply the r minus 1 times the 1 plus r squared plus, or 1 plus r squared plus r cubed, and so on. Any questions? I never pass an opportunity to do long division, because everybody loves long division, right? I may not be reading the room ever. Or it's just wishful thinking that everybody likes long division. Or I'm just hallucinating that you all like long division. Because in my mind, it's like, oh, we could also get at this result, verify this result with long division. And in my mind, everybody's like, oh, fuck yeah, long division. I don't think that's what actually happens. But in my mind, that's what I see. So I have willed it. Okay. I think what bugs me about long division is that you're told it has to go a certain way, but you could totally mess it up. As long as you're doing the right process, you really, you can't mess it up. You might end up with weird things. Like instead of writing 5 2/3, you might end up writing something weird, like 6 and -1/3. But that's okay because those are the same number. Because when we write 5 2/3, that mixed number, that's a sum. That's 5 and 2/3. And it's just another word for plus. Probably be helpful if instead of saying 5 and 2/3, especially when we shorten the and to n with the 2 apostrophes, if we said 5 plus 2/3. But so be it. This is the same quantity as 6 minus 1/3. As a mixed number, 5 and 2/3 is 17/3. If we do the division 3 into 17, the reason we put 5 on top is because the algorithm says, how many times can you subtract 3 from 17 without going negative? And we're just doing this in pieces. As long as you understand what's going on, you can't mess it up. The problem is, the first step that we ask people to do is what's 17 divided by 3? I was like, oh, that's what we're trying to figure out. You tell me what it is. But if we understand subtract is, how many times can we subtract 3 from 17? We get the design brief of what's going on in the algorithm. Subtract 3 from 17 a bunch of times. I'm going to subtract 3 from 17 6 times. 6 times 3 is 18. That's the 6 3s I'm subtracting from the 17. And it's like, oh, oops, it's -1. But what's 6 and -1 but 5 and 2/3 by another name? 6 and -1/3 is the same as 5 and 2/3. At this point, I might go, oh shit, put 1 back. There's the 5 and 2/3. That's what this 18 represents. We're subtracting 6 3s. It went negative, but that's just -1/3. We have 6 minus 1/3. A remainder of -1. We wouldn't list it that way. You really can't, you just, if you're over conservative, it works out fine as well. I know I can subtract 4. 4 times 3 is 12. 17 minus 12 is 5. Oh, shoot, I can subtract another one. So subtract another 3. Four and 5/3. 4 and 5/3. 5 and 2/3. 6 and -1/3. Same quantity. It's just that we've decided that this one is the correct one. This is how we're going to speak this quantity. And that's how we're going to write this quantity. That makes sense? It's just an agreement. We all agreed that, well, let's use this one. So we don't all come up with weird ass numbers. So if you understand the process, you really can't, you can't mess it up. How's everybody okay? All right, that's going to do it for today. I'll see y'all on tomorrow. But after day 10, thanks for playing.